Welcome to Chem 101 Lab, the week of April 23rd and April 24th. How can chemical equilibrium be manipulated? As per usual, just a couple of reminders here. Remember that Lab 8 and 9 worksheet are both due at 11:59 p.m. on Thursday or Friday in respect to your lab session. Only one person has to turn in the worksheets, and the rest of the group members will turn in the post contribution through the submission link on Canvas for your attendance. So the objective of this lab is that you will complete a 3-part procedure. After these 3 parts, you should be able to observe shifts in equilibrium system when conditions such as concentration and temperature are changed, and to be able to explain the observed color changes of 4 reactions in terms of Le Chatelier's principle. This will be the principle you guys are learning through the lab, Le Chatelier's principle. It states that when a change is imposed on a system at equilibrium, the equilibrium will shift to counteract the change. So here's an example, A plus B going towards C. A and B are your reactants and C will be your products. So if more A is added to the system, the equilibrium will shift to the right side, and here's why. Your chemical reaction is at an equilibrium, but when you suddenly put more A into this equilibrium, the reaction is no longer at equilibrium due to the ratio between the reactant side and the product side change. So the system will want to make more C to balance out this sudden influx of A, which will shift your equation to the right. If you take a look at the example in the manual, the equation here is the net ionic equation with the given color of cobalt ions being pink and cobalt perchlorate ions being blue. As many of you may be familiar with the mixing of blue and pink giving off the color purple, you can see in the description box that the equilibrium mixture is observed to be purple, which is expected of the mixing of these 2 colors. However, if you add hydrochloric acid to the system, the concentration of the chloride ions would increase as the hydrogen ions are going to be spectator ions, and you can see from the equation that chloride ions are present on the reactant side. So this would cause the equilibrium to shift to the right side. As a result of the shift, some of the pink cobalt ions would react, while more blue cobalt perchlorate ions would form. Thus, the solution become more blue. So for this lab, you would be demonstrating the principle in 3 parts. The first part would be formation of copper 2 tetrabromide and temperature effects. And part 2 will be ionization of a weak base, and part 3 will be ionization of a weak acid.
So in part 1, we'll be looking at the formation of the CuBr4 2- ion and temperature effects on this equilibrium. So we're going to combine copper sulfate, which is initially blue, and this is the source of our copper ions, with potassium bromide, which is our source of bromide ions and is initially clear. These are going to react to form our CuBr4 2- ion, which is yellow. So once we have this equilibrium mixture, we're going to subject it to a low temperature and then also a hot temperature. And we're going to use the color of the solution to determine which way the reaction is shifted, either to the left, more blue, or to the right, more yellow. It's important to remember that while the CuBr4 2- is yellow in color, it will be in equilibrium with the copper ion, which is a blue color. So if you get a shift to the right, instead of seeing yellow, you actually may see green. So here in part 1, we have 0.20 molar copper sulfate, and we have 15 mils of this. We're going to add it to our 50 ml beaker. And then we have our potassium bromide, and we're going to add 5 mils of that into our 50 ml beaker. So already we see a little bit of a color change where the copper sulfate blue color combined with the potassium bromide now turns greener. We're going to distribute this evenly between the 3 test tubes. So one test tube will be our control. That will be untouched. The next will go into our ice bath. And then the last test tube will get into a hot water bath. And we'll let these sit for about 15 minutes. So in the next part of the video, we will be viewing the part 1 results. So our 3 test tubes containing our copper 2+ ions and bromine 1- ions equilibrium mixture have been sitting in the ice bath and the hot water bath both for about 15 minutes. So you'll see that the test tube that sat in the ice water is comparable to the control in color, perhaps a little lighter, while the test tube that sat in the hot water turned green. Part 2 of this experiment is looking at the ionization of a weak base. So in this case, our weak base is ammonia, and the actual source in the experiment of the ammonia is ammonium hydroxide. And we're going to be combining ammonium hydroxide with water. And initially, this solution will be clear. So we need to add the phenolphthalein indicator, and this will help us visualize the pH. So to remember, the indicator is colorless in acidic conditions, in pink in basic conditions, such as ones that include hydroxides. So the stress on this system, we're going to add ammonium chloride, and we're going to use the color change to determine which way the reaction has shifted. So here in part 2, we will be adding 15 mils of DI water to our 50 ml beaker. And then about 2 drops of 15 molar ammonium hydroxide to that beaker. And finally, 2 drops of our phenolphthalein indicator. And this will make up our equilibrium mixture. And you'll see it turned pink to indicate basic conditions. So now we will distribute this solution equally between the 2 test tubes. So one test tube is our control, we won't do anything to that. But to this second test tube, we'll add about 2.5 mils of 2 molar ammonium chloride. And when we add the ammonium chloride, you'll see that the solution has turned pretty clear compared to the control. In part 3 of the experiment, we're looking at the ionization of a weak acid. In our case, this weak acid will be the acetic acid, and we're going to combine that with water. Again, initially this solution will be clear, so we need to add an indicator. This time the indicator will be methyl orange indicator to visualize the pH. So this indicator will be red below a pH of 3.2, orange when the pH is between 3.2 and 4.4, and yellow when the pH is above 4.4. So after we have this equilibrium mixture, we will add sodium acetate, and we will use the color change to determine which way the reaction shifted. So here in part 3, we have added 15 mils of DI water to our 50 ml beaker. And we're going to add a few drops of 2 molar acetic acid. and then a few drops of our methyl orange indicator also into the beaker. And this will be our equilibrium mixture. So you can see the color is pretty orange, which means it's a pH between 4.4 and 3.2. And we're going to split this solution evenly between our two test tubes. So we have our control, which we won't do anything to. And then our second test tube, we're going to add 5 drops of 2 molar sodium acetate. Don't worry, we didn't add any drops there. And now you can see the color change. We added the acetate and it turned yellow compared to the orange control. So here I am on your Canvas page to show you the worksheet for the Chemical Equilibrium Lab and also the rubric. So this is the submission link for the worksheet, which will contain the worksheet. So in this first question, you're actually just looking at for all 3 parts, the initial equilibrium mixtures. And then there's a series of questions asking you for the net ionic reaction and the stress and which way the reaction shifted when you added a stress. And there's also some additional questions for each part to answer. And also down here we have the rubric of the points per question.